All right, hi guys. Welcome to another video. Today we're going to be doing the Unit 10 Solutions Review Sheet. There's a total of 40 questions. So let's just get right into it. Number one, a total of 1.4 moles of sodium nitrate is dissolved in enough water to, is dissolved in enough water to make 2 liters of an aqueous solution. The gram formula mass of sodium nitrate is 85 grams per mole. Now, this one is, I would call it a little bit of a trick question because they give some unnecessary information that might kind of trip you up a little bit. And that unnecessary information is this right here. You don't actually need the gram formula mass, okay, because they're asking for molarity. And if you go to the reference table, table T, that will give you the formula for molarity. So it's molarity equals moles of solute over liters of solution, which we just abbreviate as SOLN. So here, the number of moles that we have is 1.4. So I'm just going to replace that, 1.4. And we are given 2 liters of solution. So solution goes, the liters or volume of solution goes down here. So that's 2. And we're looking for the molarity. So all we have to do is just divide these two values and we should get 0.7 molar. And that should be our final answer. Number 2, another molarity question where we're using that same formula from table T. What is the molarity of a solution of NaOH if 2 liters of the solution contains 4 moles? So it's always moles over the liters of solution. And that just comes out to 2 molar. So a 2 molar solution, so choice B. Number 3, which term is used to express the concentration of an aqueous solution? So there are 2 ways to express concentration of an aqueous solution. One is parts per million, so that's what we're going to go with. And again, the other is molarity. Number 4, based on table G, which sample, when added to 100 grams of water and thoroughly stirred, produces a heterogeneous mixture? So a heterogeneous mixture is going to mean that you've added too much solute for your given amount of water that it won't be able to dissolve it. So you will literally see crystals at the very bottom. This is describing a supersaturated solution. Again, SOLN, abbreviation for solution. So we're going to have to go over to table G. And you are going to have to just go through all of these options. So let's go do that. So we're going to table G right here. Let me just get this stuff out of the way. Okay. Let's just. Okay, there. So our first option, I'm just going to draw over here. I'm just going to write what our multiple choice was. It was 20 grams of Ki. Choice B was 80 grams of Ki. C is 80 grams of KCl. And choice D was 20 grams of KCl. So we're going to literally go through every single one of these. Okay. So I'm going to go through A and B first, where we're dealing with Ki. So there's our line. So they were also saying that we are at, for all of these, 20 degrees Celsius. Okay, so at 20 degrees Celsius, if we are at 20 grams of Ki, our line is up here, we're all the way down here. That's definitely not supersaturated, that's unsaturated. 80 grams of Ki at that temperature is still, it's here, it's higher, but it's still under the line, so that's also still unsaturated. Now I'm going to highlight my other line, which would be KCl. So here's my line. Oops, that's not good. This also is not fantastic. Oh boy, that's not good. Just pretend it's good. Okay, so there is my line. Again, we're at 20 degrees Celsius. 80 grams of KCl would be all the way up here. So we are well above our line. So this is the supersaturated solution that we're looking for. If you put 80 grams of KCl in 100 grams of water at this temperature, a lot of it would just sink right to the bottom, and it wouldn't be able to be dissolved because there's just not enough water and the temperature is just too low. So it is going to be choice C, but let's just see the other option. If we did 20 grams at 20 degrees Celsius, you see it's below the line, that's also unsaturated. So yep, our answer overall is going to be choice C. So 4 is choice C. All right. Number 5, compared to pure water, an aqueous solution of calcium chloride has what? This is the lesson, if you're watching it literally today when I post this video, this is the lesson that we did today. This is 10.6. Again, I want you guys to think about pasta water and the ice outside in the winter on the streets, okay? So the aqueous solution of the calcium chloride, right? When you add that salt to the water, you change its physical properties. And what it's going to do is it's going to raise the boiling point and lower the freezing point. So it's going to be choice D. Question 6, which sample when dissolved in 1 liter of water produces a solution with the highest boiling point? This is also something that we were doing today. Now, again, the more concentrated it is, the more ions it is going to give off into solution. Okay, so the more concentrated, the more effect it's going to have on boiling point, the higher it will make the boiling point, and the lower it will make the freezing point. So we do want something that's going to make the highest concentration. So we know that we're given 1 liter of water. 0.1 moles would give you 0.1 molar, and 0.2 moles in a liter of water would give you 0.2 molar. So it's definitely not A and it's not B, because the concentration of those would be too low. This would give you, both C and D would give you a 0.2 molar solution. Okay, but now how do we decide between magnesium chloride or potassium iodide? You also have to look at not only the concentration, but also the number of dissolved ions. So when magnesium chloride is put into water, it breaks up into magnesium and also 2 chlorines. When potassium iodide breaks up, it's 1 potassium and 1 iodine. So potassium iodide gives rise to 2 ions, but this gives rise to 3. So again, the more ions that are dissolved, the more it is going to raise the boiling point and lower the freezing point, the more it will affect those properties. So we're going to want to go with choice C. Okay. Number 7, equal amounts of ethanol and water are mixed at room temperature and at 101.3 kPa. Which process is used to separate ethanol? That's supposed to be an M. It just looks funny. Which process is used to separate ethanol from the mixture? This is talking about ethanol, which is an alcohol, and water, 2 liquids. They're both polar, so they mix nicely together. So the way to separate 2 liquids that are miscible is to use distillation, and they have to have 2 different boiling points for this to work. If they have the same boiling point, then they will both just evaporate, condense, and then end up into the same beaker, just on the other side of the distillation setup. Number 8, what is the total number of moles of sodium chloride needed to make 3 liters of a 2 molar sodium chloride solution? So this is another molarity question, okay? So what I would do is, if I get to a question and they're throwing out a lot of numbers and units, and I don't really know what formula to use, I don't know what to do with it, I would circle the things that they're giving me. So for one, they're saying, what is the total number of moles? So I know that they're giving me something with moles. They're also telling me liters. And I see 2M, that's molarity. So this is definitely the molarity formula. Okay, so I'm just going to clear all of this. I actually want to try and zoom out a little bit so I have a little bit more room on the side to write. Okay, so here is my formula. It's molarity equals moles over liters of solution. So they're giving us the molarity. The molarity here is 2. The number of moles, that's what we don't know. They're saying, what is the total number of moles? So that's X over, let me write this in like one spot. There you go. Okay. So our molarity is 2. Number of moles, we don't know, that's what they're asking us for, and they're telling us that we have 3 liters of solution. Again, if you get to something like this, a proportion, and you're not sure what to do, put this over 1 and just cross multiply, and we should end up with 6 moles. So choice D. Number 9, at which temperature can water contain the most dissolved oxygen at a pressure of 1 atm? Now you think that you might have to go to a table here, but you don't, okay? Oxygen is a gas. So all you really have to think about is the relationship of solubility and temperature for gases. Now for gases, the solubility increases when the temperature goes down. Again, this is like soda or the carbon dioxide that is dissolved in the soda. The way to get the most fizzy soda is to keep it cold and to keep it closed. So high pressure and low temperature. So the way to get the most dissolved oxygen, the most soluble, right, sort of setup is to have this be the coldest it could possibly be, which would just be 10 degrees Celsius. Number 10, which compound is least soluble in water at 60 degrees Celsius? So what we're going to need to do here is we're going to need the solubility curve. So we have to go over here to table G. Okay. And I'm going to, again, I'm going to write down our choices so that we can see them clearly here because I've switched tabs. This just makes it a little easier, I think. Okay. And again, the condition that they gave us was 60 degrees Celsius. So at 60 degrees Celsius, I'm going to find all of these lines. There is NaCl. Where's NH4Cl is right there. KClO3 is right here. And KNO3 is right there. So the one that is the least soluble is this one, the one that is lowest at this point. At 60 degrees Celsius, only about 20, you can only dissolve about 28 grams of this. And if you add any more, the water, 100 grams of water won't be able to dissolve it, okay? If you look at KNO3, for example, at this temperature, you can dissolve almost 105 grams in 100 grams of water. So this is super, super soluble, and this is definitely not as soluble. So we're gonna wanna go with choice B. Let's go back. Okay. So that was number 10, choice B. Number 11, which ion, when combined with chloride ions, forms an insoluble substance in water? So we are going to need the table, I think it's table F. So let's go ahead and look at table F. So again, I'm going to write down what our choices were. So they're asking which one would form an insoluble substance in water. Choices were zinc, magnesium, lead, and iron. So we have to look over here for the halides. That's chloride. Chloride is typically soluble except if it's with any of these things. So the only choice would be lead. If you take lead and you combine it with chlorine, it is insoluble. It will form a solid. Sink to the bottom of your solution. Okay. So choice 11 was, number 11 was choice C. Number 12, which substance has the lowest vapor pressure at 75 degrees Celsius? So we also need the vapor pressure chart here. That is table H. So let's see. So they are giving us 75 degrees Celsius. So right here. So all I need to do is just kind of mark off where everything is. Okay, so at 75 degrees Celsius for ethanoic acid, vapor pressure is 20 kPa. For water, it is, that looks like 40 kPa. Ethanol looks like it's 85. And I think that's propanol. Something on my screen is blocking it. That looks like about 180, I think. Okay, so obviously the one that has the lowest vapor pressure is right here. That's ethanoic acid. So choice 12 should be D, ethanoic acid. Number 13, which compound is insoluble in water? So again, we're going to have to go back to table F. So let's scroll. Again, I'll write down our options for our multiple choice. Choice A was barium sulfate. Okay, so here were our options. So first, I'm just going to take a look at the first one, A. So I see SO4, so sulfates. Sulfates are typically soluble, except if they're with any of these. And we actually do already have one of the exceptions. So we know that it's going to be choice A, but you really should go through all of them. If you do, you will see that all of these are soluble. Barium sulfate is the only one here that is insoluble. Okay, so choice 13 should be, question 13, again, sorry, should be choice A. Number 14. In a lab, a student makes a solution by completely dissolving 80 grams of KNO3 in 100 grams of hot water. The resulting solution has a temperature of 60 degrees Celsius. The room temperature in the laboratory is 22 degrees Celsius. That information is kind of unnecessary. Classify in terms of saturation the type of solution made by the student. So we are going to need the solubility curve. Okay, so again, the information that they're giving us is that we're at 60 degrees Celsius, and let's see, we are at 80 grams, which is, oh, I need my pen back. Again, 60 degrees, 80 grams right here. So, and we're looking at this line right here. So we are underneath the line at this point. So the way that we would classify this solution would be that it is just unsaturated. So literally all you have to do is just say unsaturated. You don't have to, write a whole thesis. Just unsaturated. That's good. Leave it like that. Number 15. As the temperature of a liquid increases, its vapor pressure does what? Okay, so this is increases. Okay, again, let's say we have a little cup of water. Okay? And at room temperature, it evaporates, but like really, really slow because there's not that much heat. It's room temperature. So there's like a few water vapor particles above it. As you heat this thing up, so if we put a flame underneath it, it's going to start to evaporate much, much faster. And there is going to be a lot more vapor here, okay? And again, the more water vapor you have right on top of the surface, the more vapor pressure you have. This is a direct relation. Number 16, recovering the salt from a mixture of salt and water could best be accomplished by, this is evaporation, also known as crystallization. So if you have a solid dissolved in a liquid, best way to separate them is to just boil it or just evaporate all of the liquid off, and then you're left with the crystals at the bottom, which is why it's also sometimes called crystallization. Okay. Number 17. What is the concentration in parts per million of a solution containing 30 grams of NaNO3 in 70 grams of H2O? So here we need the parts per million formula. Again, that is in table T. So I'm just going to zoom out a little bit so I have room on the side. So we need to calculate ppm. So here is our formula: mass of solute over mass of solution, and then everything times a million. Okay, so for this one, our solute is NaNO3. That's the thing that's being dissolved, and there's 30 grams of it, so that goes on top. Our solution has 70 grams of H2O. Okay, but they're saying 70 grams of H2O. They're not saying 70 grams of solution. H2O is just the solvent. So here you have to add the solvent to the solute. So the total solution mass is really 100 grams. Okay, so we can just simplify this and we can just say 100 grams. And then we multiply everything by 10 to the 6th. If you do this on your calculator, you end up getting 300,000. But all of the answers are in scientific notation. Again, the way to do scientific notation, there's your imaginary decimal, move it over, 1, 2, 3, 4, and 5. So it's 3 times 10 to the 5th power. So we would want to go with, oh, my bad, choice D. Okay. Number 18, an unsaturated aqueous solution of NH3 is at 90 degrees Celsius in 100 grams of water. According to table G, how many grams of NH3 could this unsaturated solution contain? So we're going to have to go over to table G. Here we are. Okay. So, all right. So they're telling us that we have NH3 at 90 degrees Celsius in 100 grams of water, which is given to you right here. And we want to know how many grams of this could an unsaturated solution contain. So here is our line. Again, this is going down because solubility of gases, ammonia is a gas. Ooh, that's really not good. This is very hard because I'm using like this little tablet, but there's no screen on it. So I'm kind of just like guessing where I'm moving. That's a little bit better. Okay. So again, we're at 90 degrees. So anything at this temperature would have to be below here to be considered, I'm going to do another color right there. It would have to be below this point to be considered unsaturated. And the only thing out of the options that they gave us would be 5 grams. So 5 grams would be like down here. That's the only point where this would actually be able to be considered unsaturated. So for what number was that? Number 18, that would be choice D. Okay. Number 19, 100 grams of water is saturated with ammonium chloride at 50 degrees Celsius. According to table G, if the temperature is lowered to 10 degrees Celsius, what is the total amount of ammonium chloride that will precipitate out of the solution? So let's clear all of this. Let's go on over to table G. Okay, so I'm going to outline this or try. Oh boy, this is really not easy, y'all. Just pretend, again, just pretend that it's like really good. Okay. So it says 100 grams of water is saturated at 50 degrees Celsius. So at 50 degrees Celsius, here is our saturation point. I'm going to call that like, I don't know, 52 grams. So about 52 grams at this temperature is a saturated solution. However, we cool this thing down to 10 degrees. At 10 degrees, there is our value. That is where it's saturated. So it's saturated, I'm going to say about 33 grams or so. So that's 33 grams. Okay. So at first it was 52 grams. Okay. But we didn't actually change anything about the solution aside, like we didn't take anything out of it. We just pulled it down. So if you go from 50 degrees down to, what was the temperature? 10 degrees. The difference between these two is going to be how much salt will precipitate out, because at this temperature of water cannot dissolve 52 grams. It's just too cold. So you do 52 minus 33, and that's about 19. Okay. So let's go see our options. So I got 19. The only thing closest to it would be choice C. Again, for questions like this, you're just going to want to go with the thing that's closest to it, because that that graph is not, super, super precise. You're kind of like just guessing your numbers. So yeah, it would be, I guess, 17 grams. Okay. Number 20, a change in pressure would have the greatest effect on the solubility of what? Pressure does not affect solids or liquids. So this is just going to be a gas and liquid. This would have the greatest effect on the gas. Okay. Let's clear this. Number 21, a mixture of sand and, one second, I'm sorry, I want to make this a little bit bigger so we can see. Okay, a mixture of sand and table salt can be separated by filtration because the substances in this mixture differ in, this would be solubility in water. So sand does not dissolve in water, so it just sinks right to the bottom, but salt does dissolve in water. So this is that example that we did in the lab, right? First, you use your filter, filter out all the sand, then you have the salt mixed in with the water dissolved in it. So that all goes through the beaker. And then you just boil off the water and you're left with the salt and the sand separated. Okay. By the way, filtration can only be used for heterogeneous mixtures, can't use it on homogeneous mixtures. 22. At STP, 2 5-gram solid samples of different ionic compounds, sorry for all the noise in the background, have the same density. These solid samples could be differentiated by their what? So they're saying that they're both at STP. So they're saying that they are at the same temperature. They're also both saying that they are 5 grams. And they also have the same density, which would mean if they have the same density and the same mass, they're also going to have the same volume. This is the only thing that would be able to differentiate them. Okay. Number 23. Also, 23 and 24 stuff we did today. Okay. Compared to the freezing point and boiling point of water at 1 atm, a 0.5 molar aqueous solution of NaCl has what? Okay, so again, whenever you add salt or any ionic compound into water, you raise the boiling point and you lower the freezing point. So we're going to want to go with choice B. This solution would have a lower freezing point and a higher boiling point. Number 24 is similar. So compared, but you're comparing two salt solutions. Compared to a 2 molar aqueous solution of NaCl, a 3 molar aqueous solution has what? So again, the more concentrated it is, which would be this one, the more effect it's going to have on the boiling, on raising the boiling point and lowering the freezing point. So this one, again, would have a higher boiling point and a lower freezing point. Two very similar questions. Okay. Number 25, at STP, which of these substances is most soluble in H2O? Now, if you try to go to table G, the solubility curves, you'll notice that only, I think, one of these is on there. So you don't actually go by the solubility curves. For this, what you have to think about is polarity. CO2 is nonpolar, N2 nonpolar, CCl4 nonpolar, HCl is the only thing here that is polar. So it has a partial positive and a partial negative side. Again, this is polar. Water is polar. Again, we have that saying that like dissolves like. So that means that things that are polar dissolve well in other things that are polar. Things that are nonpolar do well dissolving in other things that are nonpolar. But polar and polar, they don't get along. Okay. All right. Number 26. A 1 gram strip of zinc is reacted with hydrochloric acid in a test tube. The unbalanced equation below represents the reaction. Explain, using information from the reference table, why symbol AQ is used to describe the product zinc chloride. So we are going to have to go to table F, solubility. So if we look here, chlorides are typically soluble, except when they're with these three things. However, we don't have any of those exceptions. So this is just soluble. So we can just say, because zinc chloride is soluble in water. And that is all you have to say. That's why I have the AQ sign there. If this was a salt that was not soluble in water, it would have an S symbol next to it because it would be a solid. Okay. Number 27. The solubility of a salt in a given volume of water depends primarily on this is going to be A. Temperature of the water is going to be the factor that affects the solubility the most. Again, with salts, which are ionic compounds, which are in the solid phase, these typically do better when the temperature is higher. So just think about salt, okay, dissolving in cold water versus hot water, does a lot better in hot water. Number 28, based on table F, which of these saturated solutions has the lowest concentration of dissolved ions? So if you go on over to table F, you will see that this is insoluble, this is soluble, this is soluble, and this is soluble. So things that are insoluble, like AgCl, they are written like this in a reaction. They're solid. They don't actually dissolve in the water. So this is not going to break up into Ag plus and Cl minus. I mean, it might a little bit, but very, very little. Okay, so it's mostly going to give almost no ions. So the lowest concentration of ions would be the thing that is insoluble. Okay, number 29. Which physical property makes it possible to separate the components of crude oil by means of distillation? Again, this would be boiling point. Okay, just bear with me one moment. Sorry. Okay, number 30. So we are given 0.025 grams. Hold on a second, guys. I'm so sorry. Oh, loud. Okay. Sorry. Back to what we're doing. Question 30. If 0.025 grams of lead nitrate is dissolved in 100 grams of water, what is the concentration? Again, in parts per million. So we need our parts per million formula. Let's reduce this size so that we can write on the side. Again, it's ppm equals mass of the solute over mass of the solution. And again, they're saying 100 grams of water. Water is the solvent, not the solution. So you do have to add all of that stuff up. So there's the solute, that's the thing that's getting dissolved. Here's the solvent, 100 grams of water, plus this, plus the solute. This together makes the solution, and then times everything by a million. When you are done plugging this into your calculator, you should get 250 ppm. Okay. Number 31. Sorry. Okay. Number 31. What is the molarity of a solution containing 20 grams of sodium hydroxide in 500 milliliters of solution? Now, this is one like I gave in class where it's kind of like a two-step problem because, again, the moles, the molarity formula is moles over liters of solution, but they're not giving us moles here, they're giving us grams. So we first have to use this formula over here. I'll write it over here. Moles equals mass over gram formula mass. So again, we don't know the number of moles, that's X. We are given a mass, that's 20 grams. And for NaOH, I'll just do that over here. The gram formula mass, there's only one Na, one oxygen, and one hydrogen. This is 23, this is 16, this is 1. You do that, add them all up, you should get 40. So this is 40 grams per mole down here. Divide these and we get 0.5 moles. So now I can plug this in over there. So our molarity is 0.5 moles over liters. This is milliliters. To go from milliliters to liters, you got to divide it by 1,000. So that would also give us 0.5 liters. 0.5 divided by 0.5, our molarity is just 1 molar. So we're going to go with choice C. Okay. Oops. All right. Number 32. Zoom in. Okay, so a solution is made by completely dissolving 90 grams of potassium nitrate in 100 grams of water in a beaker. Temperature of the solution is 65 degrees Celsius. 32 asks us to describe the effect on the solubility of potassium nitrate, which they tell us is a solid, in the solution when the pressure on the solution increases. Now again, pressure does not affect solids, so there is no effect at all. Okay. All right, number 33. Determine the total mass of potassium nitrate that settles to the bottom of the beaker when the original solution is cooled to 15 degrees Celsius. So we have to use this information here and this to figure that out. So let's go over to table C. Okay, so the original conditions that they gave us in the little description was 90 grams in 100 grams of water. Always check that. You'll see why. We're gonna have a few questions like that. And we were at 65 degrees Celsius. And then we cooled down to 15 degrees. Okay, so we want to know how much will settle out or precipitate out. So we're looking at, again, KNO3. So that's over here. Oh, this one's going to be hard to trace. Bear with me. Okay. There we go. Okay, so again, first we're at 65 degrees, which is right in between 60 and 70, and we were at 90 grams, which is right here. Okay, so there we are at 90 degrees. This is unsaturated. At this temperature, this amount of water can still dissolve more, okay? But all this stuff is dissolved. All 90 grams is dissolved at this point. But then what we do is we cool it down to 15 degrees Celsius. So 15 degrees Celsius, this right here is where it would be saturated. So this is at this temperature, this is the most that it can hold. I would say that's about like, if you erase the line, it's above like the halfway mark between 20 and 30. So I'm gonna say this is like 27 grams. And we know that this is for sure 90 grams. So there are still 90 grams in this beaker, but at 15 degrees Celsius, 100 grams of water can only actually totally dissolve 27 grams. So the difference between these two is what would come out of the solution. So 90 minus 27, that is 63 grams. So the answer for number 33 would be 63 grams. In the answer, like manual solutions for this question, it says that the acceptable answers can range from 60 to 64 grams. So anything in between those values would be an acceptable answer. Okay, number 34. Which sample of water has the greatest vapor pressure? So let's go look. Actually, we don't even have to look here. For one, the amounts like this, it just really doesn't matter. Okay. All you have to really think about is the temperature, because the general idea is that the greater the temperature, the greater the vapor pressure. So for this one, you just have to look for the greatest temperature, which would be this. Choice D, highest temperature. Okay. Again, the more heat, the more it's going to vaporize or turn into vapor. So the more water vapor you will have on top, exerting that pressure onto the surface of the liquid. Number 35. What is the total mass of KNO3 that must be dissolved in 50 grams of H2O at 60 degrees Celsius to make a saturated solution? So let's clear this and let's go back. Something that is really, really important about this question is right here. This question is asking about 50 grams of H2O. However, if we go to table G, this is in 100 grams. So what we're going to do is we are just going to pretend that we're reading this normally. Okay, I'm going to write this down. So it was 50 grams. Wait, never mind. Okay, we want to make a saturated solution of KNO3 at 60 degrees Celsius. So here's our line, 60 degrees Celsius. I'm just going to go up until I get here, right on the line. And that's it's right over like the halfway mark. So I'm just going to say it's like 106 grams. Okay, so at this temperature and in 100 grams of water, to make a saturated solution, we would need 106 grams of it. However, they're asking how much would we need in only 50 grams of water? So that's half of this. So it's also half of this. So you divide by 2, and we would get 53 grams. So that would be, for this question, question number 35, that would be choice A. Okay. Number 36, at 65 degrees Celsius, which compound has a vapor pressure of 58 kPa or kilopascals? So we're going to have to go over to table H. So we are, let's zoom in a little bit. Okay, so we're given 65 degrees Celsius. The bottom goes by 5, so it's 55, 60, 65 is right here. And we want to know where we have to go to 58 kPa, which is right here. So we're looking at the ethanol curve. So ethanol at 65 degrees Celsius has a vapor pressure of 58 kPa. So you just have to kind of like match everything up. So for this one, number 36, we want to go with choice A, ethanol. Okay. 37, they give us all of this information. And then they give us this information down here is what we really need. Okay, they're asking again for us to calculate parts per million, but just note that it does say your response must include both a correct numerical setup and the calculated result. So for parts per million. We do the solute, that's the thing that's being dissolved, over the total mass of the entire solution. Again, notice that they're saying 1,000 grams of water and not 1,000 grams of solution. So it is 1,000 plus this. And then everything is times 10 to the 6th. So this would be your setup. And then when you do all of this, you should end up with 7 parts per million, 750. Okay. Number 38. The solubility of KClO3 in water increases as. So we have KClO3. They're telling us that it's a solid. So this is an ionic compound. Again, solids do better dissolving when the temperature is hotter. So we want to go with choice D. B and C definitely don't make sense because pressure doesn't affect the solubility of solids, only gases. Number 39. When the temperature of a sample of water is changed from 45 to 70 degrees Celsius, the change in its vapor pressure is what? So we're going to have to go to table H. Okay, here we are. All right, so we're looking at the water line right here. This is the third one. Okay, so we are going from 45, the bottom goes by, again, by 5 to 30, 35, 40, and we want to be at 45 right here. So here for water, there is our vapor pressure. It is 10. So we start off at 10 kPa, and then at 70 degrees Celsius, which is right here, and here is the water line, this is 30 kPa. So when we raise the temperature, we also have an increase of 20 kPa if you just subtract the two values. So again, for number 39, choice B, we increase 20 kilopascals. And then lastly, take a look here. Okay. Oops. Number 40. Based on table G, determine the total mass of NH3 that must be dissolved in 200 grams of water to produce a saturated solution at 20 degrees Celsius. So here's another example of where you have to really read carefully. This is saying in 200 grams of water, but table G gives us everything in 100 grams of water. So instead of dividing by 2 like we did in the other one, here we're going to have to double our answer, okay? So we're going to have to eventually multiply something by 2. So let's go to table G, okay? And I'm just going to write down the conditions that they gave us. So we're looking at NH3. Oops. A marker. We're at NH3. We're at 20 degrees Celsius, and we want a saturated solution. Okay, so we need to know how much stuff do we need. Okay, so for NH3, here is our line. Again, it's going down because it's a gas. So at 20 degrees Celsius, I'm just going to find my line. Here we are, right there. I'm going to say that that's about 55 grams. So in order to make a saturated solution at this temperature, you would need to add 55 grams of ammonia. But again, this is in 100 grams of water. They want to know how much would you need for 200 grams of water. So you would just have to double this. And so you would end up with 1,000 grams of NH3. Oops. Okay, now again, because there's not a lot of precision on this graph, right? It could be a little hard to read. There is an acceptable range, and the range is this. So what this means is that your answer could be 112 plus or minus 3. So plus 3 would be 115, minus 3 would be 109. So here is your range. Your acceptable answers could go from 109 grams to 115 grams. Okay. So again, 109 grams to 115 grams would be acceptable based on the original value that I found, 55 grams. Mine ended up being 110. If yours was not exactly 110, it's also fine. But anyways, guys, I really hope that this was helpful. And again, if you need other help, if you need, more information on one particular topic, make sure that you go to my website. You can either go to the exam review section, or you can always go to the guided notes section. And if you scroll to the bottom, you'll see a video posted for every single lesson. Okay. Anyways, good luck studying. And as long as you watch this video, you should be fine. Bye, guys.